Long before European contact, Native American societies flourished across eastern North America. They built cities, shaped landscapes, and passed down deep cultural traditions. Learning this history isn't just about the past. It's about recognizing the ongoing presence and resilience of Native communities today. Understanding Native history helps us see the full story of this land and reminds us to listen, learn, and respect the people who were here first. One of the primary ways that we learn about this history is through archaeology. Archaeologists fundamentally seek insights into the shared human experience and our collective history. Each excavation, each artifact, is a fragment of a story, one that spans continents, cultures, and centuries. Through the study of what was left behind, tools, bones, dwellings, and symbols, archaeologists strive to piece together who we were, how we lived, and what we valued. More than simply digging in the dirt, archaeology provides a method for unearthing aspects of society that, in many cases, was lost to time. It gives a voice to those who lived before us. As a science, archaeology has evolved together with other technologies which allow new insights into what we call the archaeological record. Archaeologists now commonly employ advanced analytical techniques to help solve problems, especially ones initially developed in fields such as geochemistry, physics, geology, and biological sciences. In 2013, Matthew Purtell, now a professor of geology and environmental science at the State University of New York at Fredonia, was conducting archaeological investigations of a 500-year-old house basin at the Angel Mounds Village site located near Evansville, Indiana, along the Ohio River. Dr. Purtell is referred to as a geoarchaeologist, which is someone that applies certain earth science methods to help answer archaeological questions.
Yeah, a geoarchaeologist is quite a mouthful. It basically just means that I take applications, I take approaches that are prevalent in the earth science approaches, such as soil science or geology or geomorphology, and I apply those principles and those techniques to archaeological problems. It's a way to get a more robust, complete view of past behavior by looking at the archaeological record.
Angel Mounds was one of many communities that we group under the term Mississippian. That word covers a wide range of cultures that began to emerge after AD 800 in the Mississippi and western Ohio river valleys. These communities shared certain ways of life, like advanced corn farming and building flat-topped earthen mounds for ceremonies or leadership. They also produced shell-tempered pottery and used powerful symbols in their artwork that held deep meaning. Angel was founded by around AD 1100 and grew into a major regional center. But by 1450, it was abandoned, as people moved on to form new towns and villages nearby. We don't know what the people who lived here called their city, but today we refer to it as Angel Mounds.
So at Angel, my main goal was to investigate what was called House A. And House A was the remains of a residential building where a family lived, and this was constructed within a shallow pit. So they refer to this as a semi-subterranean house. And at some point in time, people who were living in the house moved out, and it became filled in. That shallow basin became filled in with material. So my goal was to try to figure out what was the history of that infilling. What were they dumping in that shallow basin? How long did it take? And how does that reflect upon the society's rules and regulations for living within the village?
Although Dr. Purtell used several analytical approaches to study House A, something interesting turned up during what is called micromorphological analysis, which employs a petrographic microscope to inspect very small features in soil and sediment. In addition to small traces of archaeological material such as bone and charcoal, he also came across these strange little aggregates of material that were obviously different than the surrounding matrix. These little aggregates were only 1 to 2 millimeters in size and characterized dark organic material dispersed in a stringy or stretched orientation pattern. Most interesting was the presence of various voids, or areas where some previous material had dissolved or degraded. Many of these voids appear to be the remains of vegetable matter such as seeds. Others could be the ghosts of dissolved bone or perhaps even dissolved crystals. Based on the characteristics that he was observing under the petrographic microscope, Dr. Pertel started to suspect that these aggregates were minute traces of 500-year-old excrement, specifically human excrement. Several characteristics look similar to features described for relict European latrines or cesspools by other researchers. In this sense, the distinctive voids may have represented little bits of food consumed by people. Unfortunately, in 2013, Dr. Pertel did not have the proper instrumentation to make a more definitive assessment if these aggregates were indeed excrement remains.
So in many ways, the story basically ended in 2013 because I just didn't have the instrumentation to really characterize these aggregates to get a better idea of what their origin was. So I just sat there and I didn't do anything with this research. And this really all changed in 2022 when several colleagues here purchased a SEM-EDS utilizing an NSF grant. And getting this machine was really a game changer and allowed me to start to look at these aggregates in a new way.
An SEM uses a focused beam of electrons to scan the surface of a sample. When these electrons hit the sample, they interact with its atoms, producing signals that help create highly detailed images at a microscopic level. Some of these signals come from secondary and backscattered electrons, which give us topographic and compositional information about the sample's surface. When the electron beam interacts with the atoms, it also causes them to emit X-rays. These X-rays have unique energy signatures based on the elements in the sample. This is where EDS comes into play. The EDS detector collects these X-rays and converts them into a spectrum, showing peaks that correspond to different elements. By analyzing this spectrum, scientists can determine which elements are present and even their relative amounts, making SEM-EDS a powerful tool for materials analysis, forensics, and, in this example, archaeology.
Yeah, basically the SEM-EDS results were very intriguing because they, in essence, helped validate thoughts that I had had 10 years prior, that these aggregates were indeed enriched in the elements that you would expect to see if they represented excrement.
The results showed that the aggregates were enriched in aluminum, iron, potassium, phosphorus, and calcium. Such a composition is consistent with expectations for human excrement and what has been documented for latrine and cess areas. The enrichment of phosphorus and calcium is especially stark when compared to the surrounding material. Another finding was the realization that along the margins of several voids, there is phosphatic mineral growth. Phosphatic minerals, likely representing crandallite, biogenic apatite or carbonate hydroxylapatite, form through a phosphatization process of an organic-rich solution, and such secondary minerals are commonly associated with human organic waste decomposition.
Yeah, if these aggregates are indeed excrement, and they're human excrement, as opposed to an animal dung, it is very intriguing because we actually know very little about the sanitation practices and technologies of Eastern North American Native American societies. You can learn a lot about a culture based on how they regulated their organic waste disposal. And we just don't know much about how people in the Eastern United States did this. And so this could be a very significant finding.
Since SUNY Fredonia acquired the SEM-EDS system in 2022, it has transformed the way our researchers explore long-standing scientific questions, unlocking entirely new approaches and insights. Faculty members have been applying this powerful tool across a wide range of topics, while actively involving both college and high school students in meaningful hands-on research. These are opportunities rarely found elsewhere, and we're proud to be offering them here. We look forward to sharing more exciting discoveries with you soon.